Hello and welcome to this video on phasor diagrams. If you haven't watched our previous video where we introduced the topic of phasor diagrams and how they're constructed, I would suggest going back to watch that first. But in this video and in a subsequent video, we're going to apply the principles of phasor diagrams to some simple circuits and show how the voltages and currents in those circuits can be represented on phasor diagrams. So to begin with, I want to look at this circuit we have here on the screen. We've got a simple series RL circuit with an AC power supply or an AC voltage source. So we have 100 volts, 50 hertz AC source here, connected to just two components in series, a resistor of 20 ohms and a 50 millihenry inductor. What we're going to do is we're going to calculate the current that flows in this circuit. It's a series circuit, so there's only one current flowing. And to do that, we first need to calculate the impedance of the circuit. So before we can do that, we have to look here at our inductor, which is a 50 millihenry inductor, and that inductor has a reactance. If you haven't watched our videos on calculating things like reactance and impedance in simple circuits, then again, I would advise doing that first. But in this case, our reactance we can express as XL, the reactance of an inductor, and the formula to calculate that reactance is 2 pi FL. So in this case, that's 2 pi multiplied by the frequency in this circuit, which is 50, multiplied by the inductance, which is 50 times 10 to the minus 3. And if we calculate that, I come out with an answer of 15.71 ohms. Now, one thing to remember, and again, this is going back to when we discussed impedance in AC circuits, is that impedance is a complex number and it's made up of a real component, which is resistance, and an imaginary component, which is reactance. So if we were to express the impedance Z of this formula as a complex number, it would be 20, our resistance, plus the reactance, which is the imaginary component. So in rectangular form, that's a J 15.71 as our reactance there. So the impedance of the circuit is 20 plus J 15.71 ohms. Now again, that impedance we can express in polar form rather than in rectangular form, and we're going to use that polar form in just a moment to calculate the current in this circuit, which is also going to be in polar form. So it is possible to convert from rectangular form to polar form by using most scientific calculators, which have a polar form function. In this particular instance, I want to show how it's done sort of manually, as it were, and we do that by representing this by an impedance triangle. And the impedance triangle has resistance on the x-axis, as it were, and reactance on the vertical or y-axis, and then the resultant of the two is our impedance Z. So we know that our resistance is a resistance of 20 ohms. We know that the reactance now is 15.71 ohms. We want to calculate the magnitude of this impedance here, and we also want to calculate the angle that the impedance has from the horizontal. So this angle marked here, we're also going to calculate as well. So to do that, we're going to do two things. First of all, we're going to use Pythagoras' theorem to calculate the magnitude of that impedance. We're going to say that Z squared is equal to R squared plus X squared, because they form a right angle triangle, as it were. We can move our reactance over to this side, for instance, rather than on this side. We can move it over here, and now we have a right angle triangle. And so Pythagoras' theorem can be used in this instance. Anyway, by working that out, so that would be 20 squared plus 15.71 squared, which would give me Z squared, and then square rooting that would give me a result of Z, which I'll just skip to here, and Z comes out as 25.43 ohms. The last thing to do is to work out this this angle here marked on the diagram, the angle from the horizontal. And again, we can use a little bit of basic trigonometry here, because we know the tan of that angle is the opposite over the adjacent. And so what we can do is we can say that that angle is equal to tan to the minus 1 reactance over resistance, and that comes out with an angle of 38.15 degrees. And so finally, our impedance that we said up here in rectangular form was 20 plus J 15.71 can also be expressed as 25.43 at an angle of 38.15 degrees, and that's an impedance, so it's measured in ohms. So these two expressions for impedance are both exactly the same, as it were, but one of them is in rectangular form, one of them is in polar form. From now on, and in subsequent examples, we probably won't go through all of this derivation. We'll simply just convert from one to the other just for time's sake. So returning to our example here, it's the current that we want to calculate in this particular circuit. So I'll mark that on here as I, the current flowing through this series circuit. And we're going to calculate that current just like we would calculate any other current using Ohm's law. The only difference here is I want to keep my calculations as a complex number, particularly in polar form, because these angles and magnitudes that make up polar form I'm going to use as part of the phasor diagram later on. So we can say for polar form that current I is equal to voltage divided by resistance, or in our case voltage divided by impedance. It's not just a resistance in our formula. And our voltage is marked as 100 volts, and because it's our supply voltage, we're going to assume that that's a reference voltage of 0 degrees. If it doesn't say otherwise, then we're going to assume that that supply voltage is at 0 degrees by default, as it were. Divided by our impedance, which you just calculated in polar form, it was 25.43 at an angle of 38.15 degrees. Remember, when we're dividing in polar form, it's very easy. We simply divide the two magnitudes, so it will be 100 divided by 25.43, and we subtract the angle, so 0 minus 38.15. So our current in this case is going to come out as 3.93 at an angle of minus 38.15. And because it's a current, that's measured in amps. Now that we've calculated the current in polar form, we're going to represent the voltage and the current in this circuit on a phasor diagram. And the way we do that is by remembering two things. First of all, that we always represent our phasors as beginning in a horizontal direction. So if I draw a quick arrow on here as a phasor diagram, our phasors emerge from a given point, a central point, and by default, as it were, they point to the right in a horizontal direction. And so we begin with our reference phasor in this direction directly horizontally to the right. Anything that has a leading phase angle or a positive phase angle is going to tilt upwards from that horizontal position. Anything that has a lagging or a negative phase angle is going to tilt downwards from that horizontal position. So what we're going to do is we're going to represent our circuit here, like I say, as a phasor diagram, and I'm going to begin by marking our voltage on, which is a reference phasor, so it's going to point directly to the right, and I'm going to mark that on as being 100 volts. So I'll put that on there, 100 volts, as our supply voltage, Vs. And the second thing I'm going to do, which is the only other thing in this circuit, is our current. There's only one current, and it's 3.93 amps, at an angle of minus 38.15 degrees. Now, I don't have a protractor to hand, and this is just going to be a rough guess, but you can see the general idea. I'm going to mark on this angle as being my angle is going to be at 38.15 degrees, tilting downwards because it's a negative angle, and I is equal to 3.93 amps. So there we have a very simple phasor diagram which explains what's going on in this circuit. We have one voltage, we have one current, and the current lags the supply voltage by 38.15 degrees. Let's now have a look at an almost identical example, another series circuit, but this time we have a series RC circuit. We've got a resistor and a capacitor this time in our circuit, and we're going to apply a very similar process. First of all, we need to calculate the reactance of our capacitor, and for that we use the formula XC is equal to 1 over 2 pi FC. And substituting some values in there, we have 1 over 2 pi times 50, the frequency of our supply, times 220 times 10 to the minus 6, because it's in microfarads, and that's going to come out as being 14.47 ohms. Now, in previous videos or in some other texts and online websites and such like, you might have seen this formula given with a -1 on the top of the fraction. Some texts don't have it and some do, but the important thing to remember is that when we express our reactance as part of an impedance in a complex number, we do have to include that minus term. Let's see what I mean. So Z, just like before, is the complex number combining the real term resistance and the imaginary term reactance. The only thing we have to remember in our case with capacitance is that it's a minus J 14.47. Now that might have already been taken into account if you had a minus on the top of the fraction there. It would just make this answer a minus number as well. Even if that isn't the case, if your formula doesn't have a minus on the top of the fraction, you still have to remember to make our minus J term here for capacitance, which always has a negative reactance when it's expressed as a complex number. That's going to affect our answer for the next stage, because when we convert this number to polar form, it's going to be at a negative phase angle. We're not going to do the conversion like we did in the previous example, where we used Pythagoras' theorem and trigonometry. We're just going to go from straight from one to the other. 20 minus J 14.47 is going to be expressed in polar form as 24.69 at an angle of minus 35.89 degrees, and that's an impedance, so they should both be measured in ohms. So finally, we're going to do the same thing as we did previously. We're going to calculate the current in this instance, again using Ohm's law, voltage divided by impedance, and here we can say that the voltage again is our sort of reference supply voltage, 100 volts at an angle of 0 degrees, divided by our impedance, which now is 24.69 at an angle of minus 35.89. Remembering that we divide the magnitudes, we subtract the angles, we're going to come out with a result of 4.05 at an angle of 35.89 degrees, and that's a current, so measuring amps. Lastly, we're going to do something very similar. We're going to plot our very basic phasor diagram, which has a reference phasor, the supply voltage in this case, which is 100 volts, and now we have a current that has a positive phase angle, 35.89 degrees, and so our current is going to tilt upwards from the horizontal by 35.89 degrees. This diagram is obviously not to scale, but hopefully you get the idea. There's our current, and it has a value of 4.05 amps. So in this first example video, we've been looking at RL and RC circuits, and we've looked at both series RL and RC circuits. But in this last little circuit here, I want to look at an example of a parallel circuit, and that changes a couple of things for us. First of all, now there's more than one current in the circuit. We have, I can mark on here, a current going through our resistor branch, which I'm going to call IR. We have a current going through our inductor, which I'll call IL, and then together they combine to form a supply current, IS. So we have more than one current to express on our phasor diagram. Let's begin by looking at our circuit in the same manner that we did so before, because we find actually the component values are the same as the first circuit we looked at. And so we know the resistance 20 ohms, and we know the inductance 50 millihenries. We also know the reactance XL, because the frequency hasn't changed in this particular example. We calculated the reactance of our inductor to be 15.71 ohms in our first example, and that's going to be the same in this instance. So what we're going to do is we're going to apply Ohm's law again to the different branches of this circuit separately. We have a 100 volt supply, which is connected across our resistor, and it's also connected across our inductor in parallel. And so we're going to treat those separately to calculate IR and IL to begin with. Let's calculate IR first of all, because that's probably the easiest. And again, we're going to use Ohm's law. So IR is simply V over R. There's only a resistance in that branch. Now, these are all real numbers. 100 volts, resistance is a real number. We could calculate this without having to use complex numbers at all, but just for the purpose of consistency, I'm going to keep this in polar form, but it'll be very easy because our voltage is 100 volts at an angle of 0 degrees, and our resistance is 20 ohms, also at an angle of 0 degrees. They're both real numbers without any phase shift at all. And so what we're going to get is our result of 5 amps at an angle of 0 degrees as well. We're going to do the same for IL now. Now, something to bear in mind is IL is traveling through our inductor here. And so our inductor is not a real impedance at all. It's an imaginary reactance, or an imaginary component of our impedance. And so what we're going to say is that first of all, our IL is going to be expressed as voltage over reactance. And just as a sort of side note here, our reactance is going to be J 15.71. If I was to express that fully as a complex number, it would be 0 plus J 15.71. Now, if we calculate that in polar form, that's the same as saying 15.71 at an angle of 90 degrees, because we only have the vertical component in our impedance triangle. We don't have any horizontal component, and so these two are equivalent, as it were. Anyway, let's get rid of those for now and go back to the equation in question here, because voltage divided by reactance, we're going to use the same supply voltage as we did before, that 100 volts at an angle of 0 degrees. So we can say as a fraction here, 100 at an angle of 0 divided by 15.71 at an angle of 90 degrees. And so likewise, like we did before, we divide the magnitudes in our fraction there and subtract the angles. We come out here with 6.37 at an angle of minus 90 degrees. So now we have two currents in our circuit. We've said that IR is 5 at an angle of 0 degrees, and we've said that IL is 6.37 at an angle of minus 90 degrees. Together, those two currents IR and IL combine or must add together to form IS. IS is what supplies both of these currents, and they join together to form that same supply current. So the addition of IR and IL must be IS. So one of the last things we're going to say before we plot our phasor diagram is to say just that IS is equal to IR plus IL. So in polar form, we would be saying that that is 5 at an angle of 0 degrees plus 6.37 at an angle of minus 90 degrees. It becomes very difficult to add numbers in polar form. It's a bit easier to convert them to rectangular form and then add them. So what I'm next going to do is express those in J notation or rectangular form. And for these particular examples, it's quite easy because 5 at an angle of 0 degrees is the same as saying 5 plus J0. We only have the horizontal component, the real component. We don't have anything in the imaginary component. Plus 6.37 at an angle of minus 90. We can say that that's 0 for the real component minus J 6.37. We have 6.37 going downwards in the rectangular component. And so when we add those together, obviously our J0 term disappears and our 0 term disappears. We're left very simply with our term, with our supply current rather, in rectangular form, and that's going to come out as 5 minus J 6.37 amps. Now that I've calculated the supply current in rectangular form, I want to convert it to polar form. Polar form means that it's going to be easier to plot on my phasor diagram. And so, very simply, if you've got a scientific calculator to convert from rectangular to polar, it's easy to do so. Or by using the trigonometric methods we talked about earlier, we can do the same. But in polar form, IS is going to be expressed as being equal to 8.10 at an angle of minus 51.87 degrees. And so the last step for us is to draw our phasor diagram. And so if we go back up just a little bit here, hopefully we'll be able to see all of these terms and draw our diagram appropriately. I want to start, like we've started with all our other diagrams, by drawing our reference phasor first, which is our supply voltage, so Vs, 100 volts, and that's going to point directly to the right. We have two currents to begin with flowing through two separate branches. We have our current IR, which was 5 at an angle of 0. So anything at an angle of 0 is going to be in a horizontal direction in line with the reference phasor. So I can draw on my my current IR in the same direction as the reference phasor, like so. So we'll see here I've got IR, and that is 5 amps. We've also calculated the current going through the inductor to be 6.37 at an angle of minus 90. And so remembering we take all of our angles from that horizontal starting point, minus 90 is going to be pointing downwards from the horizontal at 90 degrees. And so we'll end up with something like this, where I've got IL, and that's 6.37 6.37 amps at an angle of 90 degrees downwards. Notice as well what I've tried to do, now that I have more than one current, I've tried to draw them to scale. I've not done a very good job, and I'm sure when you carry out your own examples you'll do a bit better job than me, but here a current of 5 amps and a current of 6.37 amps, these vectors or these phasors, the length of the actual arrow should correspond with the size or the magnitude of the current in question. I don't need to be scaling my currents to my voltages because they're two different quantities. If I had more than one voltage, I would certainly need to get those to scale with one another, and likewise I want to get my currents to scale with one another as well. So my vector here for IL is slightly longer than that for IR, 6.37 compared to 5. The last thing I want to mark on is the supply current, which is the resultant of both the currents IR and IL. And so what we'll actually find is if we had drawn this diagram perfectly to scale, with all of the angles absolutely correct, which mine by no means is, but if I had done so, I could actually measure the distance and angle of the resulting phasor, which is the addition or combination of the two that I've already marked on the diagram, and that would be IS, the supply current. As it happens, we've already done this mathematically down the side here. We've calculated our supply current to be 8.1 at an angle of minus 51.87, and so if I had drawn this diagram a bit better than I have done here, would find that that would correspond, this marked angle here would be 51.87 or minus 51.87 I should say, but 51.87 in a downwards direction, and this length on the diagonal would be 8.1 amps. So I hope you found this video useful on applying the principles of phasor diagrams to some simple series RL, RC, and then a parallel RL circuit. Calculating the currents in complex form, in polar form, and plotting phasor diagrams which represent the magnitudes and the phase angles of those currents and voltages. In the next video, we're going to look at some slightly more complicated examples again, which involve RLC circuits, circuits which contain resistors, inductors and capacitors, and we're going to apply the same principles there as well.